All right, we're back for the next one, and before we end up pushing into RL circuits, I'll mention a little tiny bit about what mutual inductance is about. You're not going to see this on any of your any exam or something, but if we have one coil that's over here, and we have another one that's over here, and we end up changing the magnetic, we change the current through this one. So when we do that, we'll end up changing the number of field lines, of course, that's going through there. We end up having the regular inductance stuff we've talked about before. But remember that your magnetic field is not does not have a start and end point. So we said before, there's no particles with a north charge, no particles with a south charge. So if we end up having current that's inside the solenoid that goes like this, that the field line will loop back around. Let me try to keep it in frame. So it will loop back around. So if there's another thing over here, then some of those lines will go through something else over here. And in that situation, you will end up getting a change in the number of field lines through this other thing, which is not attached to your main current source. But that can end up then inducing an EMF in something that's separate from it. The only that if we have a little time at the end, I may end up talking about something that's kind of interesting that can be a result of mutual inductance. But again, that will not be on there. Your text ends up using a capital M for it. The computation to end up finding it is maybe technically within the scope of the course, but it would be really nasty to try to end up coming up with it, and we're not going to end up bothering at all. So you're not responsible for that. The unit is still in Henry's. It normally is something that you don't want. So inductance is sometimes something you do want because you want to be able to run a motor and stuff like that. But usually mutual inductance is not a good thing. All right, so we will next turn to what happens. So, and remember when we introduced resistors, we already had capacitors. So we said, okay, what happens if I have a resistor and a capacitor that I hook up in a circuit? We had our timing circuits from that before. So now we're going to do something similar. So we're going to end up having a battery, and I apologize for the drawing. There was a little scratch in it. So in terms of reading it, what that little thing in the upper left-hand side is, it's just like what we did before whenever we did Kirchhoff's law, that you choose an arbitrary point as being where you're going to call your zero. So you could say that's where you ended up setting setting a ground wire or whatever. And then you follow your EMF changes as you go around the loop. Potential difference changes. Same meaning, different word. So, so as we end up moving around that loop, that as we go down from that point in the upper left, we have a battery. Top of it is your negative terminal, bottom is the positive terminal. We keep going around, we end up getting a coil at the bottom. The reason for the plus and minus we're going to get to, so don't worry about that quite yet. So why was that there? We'll derive where those come from in a second. Then we keep on going. We have a resistor. We know how to deal with that. We have a switch. So that's what our circuit will look like. So what we want to think about is what's going to happen when we close a switch. Very much like what we have with a charging RC circuit. So we've seen this sort of thing before. All right. So in this situation, when I do close the circuit, remember what an inductor will do. An inductor, as far as the inductance is concerned, it tries to fight the change in the current. Never wins, it only fights it. So because it doesn't win, we can figure out which direction the current will go, which would be the current that you'd get if it wasn't there. So we end up closing the switch. We otherwise know current will go from the minus side to the plus side. Remember, an inductor coil, it's a wire, right? So it's a conductor. It's not an insulator. So it's not like a capacitor. So the current ends up being able to go through inductor completely fine. Spins around the loop. So you're able to figure out that's the reason we know which direction the current is. So we know which direction to end up, which side of the resistor is positive and negative. Then when we look at my inductor, the inductor is going to end up inducing an EMF that's trying to oppose, at least while it's in the introductory phase, is going to try to oppose the current. And so then you end up getting an EMF in the opposite direction, so an EMF that's trying to slow the current down, which is why the positive side of the inductor EMF will end up being against the positive terminal of the battery in the drawing. So that's the reason for that. So now we can end up doing a little bit of writing Kirchhoff's first law. So as we end up going around the loop from the point I marked with an X, we'll end up going in the path following the current. We didn't have to, but that's an obvious choice. So if we go around that way, then the first thing we come to is our potential difference. The way I've drawn it, that will be positive as we pass through it. Going down, then we go to the right across the inductor. Notice you go from plus to minus. You have a minus sign there, so it's minus L di dt. Then we move past the resistor, minus IR time equals 0, because we go all the way around and we end up getting to the start point. So then we clean this up. We end up moving my constant potential difference to one side, and then we end up doing one of the little tricks that you get in calculus by using an integrating factor. That again, if you in diffie-hughes, if you haven't had differential equations, don't worry excessively about it. You can check to see from the total derivative on the second line that if you end up going backwards, you can get to that to di dt equals r over L times I equals delta V over L. So there's a way for you to be able to get there if you don't know it, but if you've seen this before in diffie-hughes, then it's just a regular method. We take the integral at the last step. So when you take the integral, from delta V over L becomes delta V over R, because when you take the derivative of e to the R over LT, the R over L ends up coming out in front, and let's see, yeah. So yeah, that you'll get your the terms out, and whenever you get to your the current expression, you'll have that constant integration to end up figuring out how to deal with it. It was a charging circuit, so at time 0, when you close the switch, there wasn't any current. So that's what you end up plugging in there. So that gives you your constant integration is minus delta V over R. And then your current, then you factor out your delta V over R, and you get the expression that you have in there, 1 minus e to the minus R by L times t. So as your time goes to infinity, then your current gets closer and closer to delta V over R, which again, remember we say that the inductor fights but doesn't win. So eventually it completely loses because the current's constant. And so it's as if it's just now a piece of wire going across there, and your resistor then is the only source of slowing down the current. So that's why you get, as time gets really big, you get that. So it should be what you'd expect. Then if you look at the form, this should look pretty familiar in terms of a current, because this would look, it's not exactly like what you would have seen before, because that looks more like what a charging current would look like. Charging, for a capacitor charging the charge would look like. It's not RC, but it's going to be that R over L times T. So we end up having something that's similar. So this also is a timing circuit, and we end up doing it the same kind of way, e to the minus t over tau. We end up introducing a time constant for your RL circuit, and that will be your inductance divided by the resistance. So the bigger the resistance is, the faster it gets to equilibrium. And in terms of understanding why that's true, if you got big resistance, you're not going to have a whole lot of current at the end. So it's not going to change much because there's not much to change. It goes from 0 to something small, right? So it doesn't. So the EMF generated by the inductor coil is not going to fight it as much because there's not as much change. The bigger the inductance is, the harder it fights. So that's the reason that will be in the numerator, and that ends up giving us why we get that expression. Then let's see. I think we'll break here and then we'll come back and talk about energy storage in the next one.